Thank you very much, Vivek, for this very pleasant for me and very flattering introduction. It's a pleasure to welcome you all today. Thank you very much to Quantitative for this opportunity to speak. I see we have an enormous number of participants today. I would like to say hello to all of you. Thank you very much for coming to this event, and thank you very much for listening to what I'm about to say. I hope that you will find this interesting. You will see logos of Talesians and Imperial College London, organizations that I represent, but I wanted to say that I'm associated with, but today I'm not actually in any of those capacities, so I'm just giving a talk on behalf of Quantitative. I want to really tell you a little bit about what reinforcement learning is. This is an important branch of machine learning, and I want to really explain to you how this works and why it is important, in particular at this time, to learn this subject, why it is so helpful, and why it will be very, very interesting for you, why the times are very, very interesting for people now who are working in finance, but also who are getting into this field, why it's important to really understand these subjects and how this can further advance your career and put you ahead and help you really make a big difference through your professional activities. What we see here is a picture that represents the Industrial Revolution. So you will see all these, basically all these pipes, all this smoke that is being produced. This is mechanics. Essentially, Newton has just introduced, maybe a little while ago, he has introduced mechanics through Principia Mathematica, and people are beginning to use machines for the first time as part of, for example, factory works. This is what we see here is Wentworth works, which were working in metals. But as you can see, there is a positive side to it. There is new industry, there is production going on, but there is also pollution. And there are all these things that were associated with the first stage of automation, with the Industrial Revolution. The machines that we're talking about here are relatively unintelligent. They can do some mechanical stuff, the kind of stuff that people can do with ease, but now they can do them at scale. So what is happening here, we have made this first step towards automation, and that was done in 1760s. Up until 1830, that was largely confined to Britain, and then gradually the Industrial Revolution started to spread to the entire world. And it's associated with very specific technologies, with very specific things. There are new basic materials, there is iron, there is steel, there are new energy sources, things like that, right? So this is the beginning of automation, and this picture itself comes from a private collection, and actually from the Everett collection, and it represents Wentworth works. The culmination of the Industrial Revolution, I sometimes teach at Imperial College, which is very close to Hyde Park, and in 1851, in very close to Imperial College in Hyde Park, there was this massive structure, which is the Crystal Palace, where the great exhibition of the works of industry of all nations took place. And that was, if you like, the apex of the Industrial Revolution. There were hundreds of thousands of objects, inventions, machines, creative works, and so on. Joseph Paxton designed this Crystal Palace. It has since been moved out of Hyde Park. It burned down eventually, but I mean, this is where over 500,000 people came to Hyde Park to celebrate the great exhibition, to really look at all those objects invented. A lot of people attended this event, what was actually done during the Industrial Revolution, but we are nowadays out of that age. The second stage of automation started perhaps in the 1950s, and we went, and before that, in between the Industrial Revolution and the digital revolution that we're looking at here, there was another development. There was electronification. So we went from mechanical machines to electrical machines. And the second stage of automation was about, these are still machines, and these are still enabling us to do things at scale, but they are different. They're more intelligent. Then they can play chess, for example. You can interact with them uh, as say video games and so on. They can do some not necessarily physical work for you. They can do some intellectual work for you. They can help you with word processing, for instance. So this digital revolution, um, it also heralded the beginning of a new age, the information age, which is a historical period characterized by this rapid shift from the traditional industry established by the Industrial Revolution to an economy which is primarily based upon information technology. So, those of you who are old enough to witness the entire thing, I mean, I've witnessed much of it, right? So, you will probably remember the first TCP/IP messages. You will remember Microsoft being founded, Walkmans that used to predate iPads and so on, and ultimately going up to sort of the 2010s when more than a half of the global population was connected to the internet. And there is more to do, right? And there is the next logical step. You can program these machines, right? You can give them goals, you can give them tasks to do. But when you program these machines, you have to be very specific. And back in 1969, during his Turing Award lecture, Marvin Minsky said that computer languages of the future will be more concerned with goals and less with procedures specified by the programmer. This is currently not the case today for most systems that we interact with. But if you think about systems such as ChatGPT, then already we're beginning to interact with machines in very different ways. We're beginning to discuss goals and objectives with machines, and machines are now not only automating the various steps, they're being used as planning devices, and they're delivering these results intelligently. So we are now in this era of intelligent machines. And the pioneer of computing, Alan Turing, wrote in his 1948 paper about basically about the pain pleasure stimulus. When a configuration is reached for which the action is undetermined, a random choice for the missing data is made, and the appropriate entry is made in the description tentatively and is applied. When a pain stimulus occurs, all tentative entries are cancelled, and when a pleasure stimulus occurs, they're all made permanent. So we have this notion, a new notion of a hedonistic learning system that learns through reward and punishment, much like humans do. Okay, so these two people, Sutton and Barter, were among the pioneers of this new branch of computing, which they initially referred to as a hedonistic learning system. And they spent their academic careers on this when they realized that it was this simple idea, the idea of a learning system that wants something that adapts its behavior in order to maximize a special signal from its environment, a hedonistic learning system, or as we say nowadays, reinforcement learning. So when you think about machine learning, you can subdivide it, perhaps somewhat tentatively, into several sub-areas. You can talk about supervised learning, you can talk about unsupervised learning, and reinforcement learning is distinct from these branches of machine learning, but at the same time, it does significantly overlap with them. Also, when you think about what kind of background do you need to really work in this field, it's quite cross-disciplinary and it spans computer science, neuroscience, psychology, economics, mathematics, and engineering. And it's, if you if we kind of zoom into this inner circle, we'll see that there are several disciplines which are very closely related to reinforcement learning. Apart from machine learning, of which it is a part, there are the disciplines of, excuse me, optimal control, reward systems, operations research, classical operant conditioning, and we have bounded rationality as well. It's a very different, very new way of thinking about computing. And since many of you are interested in finance, it's a new way of thinking about finance. And so let's have a look. So reinforcement learning does not require you to know the exact recipe. So unlike, for example, the classical work by Black, Scholes, and Merton on options pricing, you really needed to work out how to hedge that option. You had to work that out analytically by solving parabolic PDEs, and it's not an easy task, right? No, it's also it was very lucky of them to be able to find this closed form solution. Most PDEs don't have closed form solutions, and most PDEs they're not soluble just like that, and they had to make quite a lot of assumptions about the way the market operated, about the way the market frictions operated to solve the Black-Scholes PDE. So what if you don't have that kind of nice platonic environment? What then? What happens then? Well, this is where reinforcement learning comes into play. You don't necessarily need to have an exact model. You just need to have something, some sort of an environment where you see feedback from the environment. So you can make money, you can lose money. That can be your feedback if it's financial. So you work with this evaluative feedback rather than the true values, the ground truth, and your system learns as a consequence of receiving this evaluative feedback. And this is something that you can do in many different environments. So it's actually a very, very powerful idea. So it has some similarities with unsupervised machine learning because we don't really rely on examples of correct behavior. Remember, you have evaluative feedback, but it's not really unsupervised machine learning. Reinforcement learning is concerned with maximizing a reward signal rather than trying to find hidden structure, as distinct from unsupervised machine learning. So what are the ingredients if we are to consider a classical machine learning setting? What are the ingredients? Well, first of all, we have the agent that makes decisions. Now, the very word agent can evoke a lot of philosophical discussions as to whether we have true agency or that agency is only an illusion, whether we have free will or that free will is an illusion. We are going to sidestep those arguments, and we are going to kind of assume that the agent has some form of agency, hence the name agent. And the agent doesn't work in isolation. The agent interacts with the environment. Okay, so and the way the agent interacts with the environment is by taking actions. So you can see that this paradigm of reinforcement learning, it's a paradigm where it has a certain computer science feel to it, right? We are kind of thinking about these ideas fairly abstractly. We don't necessarily need to go into a lot of economic modeling to really understand what's going on, but we have to introduce these key ideas: agent, environment, actions. And the agent also receives observations from the environment about changes in the state which may be caused by the agent's actions, or maybe directly or indirectly, or maybe unrelated to the agent's actions. Perhaps some other agents are interacting in this environment, and we have a multi-agent system. But the classical thing, the classical setup in the reinforcement learning world is that the agent takes an action, say action A, T at time T, and the environment responds with two things. It responds with a state change. So we are now in a new state, ST plus one. And in addition to this, we also get the reward RT. There are different conventions. So sometimes the reward in response to action AT may be RT+1, but we'll stick with this specific convention. So somehow we need to be able to reason about the sum of all rewards going into the future. So we may get this infinite sum or finite, depending on whether this is an infinite kind of interaction or not. And we have this sum of all these rewards that we receive over time going into the future. This sum may or may not converge, but fundamentally, if we have any convergence issues, it's mathematically convenient to introduce the same trick that is introduced in finance, which is called discounting. So we introduce this discount factor, which is typically somewhere between 0 and 1, which means that the rewards that I receive now have more weight to me than the rewards that I receive in the future. And it's also a useful mathematical trick because it enables the convergence of these infinite sums. And then we make this assumption, which not necessarily represents reality, because when we think about the reality that we are in, it's perhaps even more terrifying than the reality that this agent finds itself in, because we have to take care of many, many different things. They're not just financial, there are physical health objectives. We need to basically take care of interests of many different people. And so this is somewhat dubious because not everything can be reduced to a single number. But if it were, then we would have this reward hypothesis. All goals can be described by the maximization of expected total reward. Okay, and that's the assumption that is usually made in the world of reinforcement learning. Thus, we have an agent that interacts with the environment by being in a certain state, state 0, taking action A0, then receiving the reward R0, moving into state S1, performing action A1, and so on. So we have this SAR thing, right? So that's like we have this sequence of this is why one of the algorithms of reinforcement learning is known as SARSA. So the agent um, may not know the exact state of the environment. So it may have an idea, some sort of an approximation, maybe an inaccurate approximation of the state of the environment. So the agent state and the environment state may not necessarily be the same thing. And in chess, every agent knows exactly the state of the environment. In the game of poker, we don't really know. We have some sort of a probabilistic notion of the environment. So this is why chess is a perfect information game, whereas poker is not. So then another key concept, and please excuse me, I'm introducing all these ideas. I have to do it just to kind of give you this tool set, right? Just to give you all these tools that you need to use to be able to think in terms of these techniques and solve problems in terms of these techniques. We have this notion of policy. What's a policy? It's a map from state to action. If I'm deterministic, then whenever I'm in state S, I'll always take action A. Or it may be some sort of a stochastic function. So whenever I'm state A, I may take one of several possible actions. So we can think of policy then as a probability distribution, as a conditional probability distribution, or indeed as a probability measure. So let us now kind of say, okay, we are building our apparatus so we can reason about these things. What's the next thing that we need? Well, we need a key thing. You know, who said this? One of these people, I think it was Drucker, who said that if you can measure it, you can manage it, right? So if you can measure it, then you can influence it. And in general, in business and life, you measure things so that you can actually influence them. So, for example, someone who is unwell, they would be taking their temperature measurement so that they can hopefully bring the temperature to a healthy level. Okay, it's the same with finance and with reinforcement learning. So what we want to be able to do, we want to be able to ascribe values to state. So we want to be able to tell, is it a good state for us or is it not so good state for us? And how do we do that? We assume that we always follow the same policy, pi. So it only really makes sense to talk about the value of the state, provided we are continuing to follow this policy pi. And then what we do, we compute the expected return, right? We compute the expected return if we start from the state S and if we follow this policy pi. We add up all these expected future rewards within the expectation operator, and that gives us this value v pi s. Of course, we don't need to be in the future. We can compute the expectation as of now, condition it on the fact that we are in the state S, and that tells us how good this state is. Again, how good the state is under this policy pi, right? And that's a fundamental thing. That's the value function. That's how we value states. And then we may need a model. A model predicts what the environment will do next. We don't always have a model. We may have a black box environment that we can interact with. So, but if we have a model, if we are lucky, then we can use these model-based algorithms where the model, part of the model predicts the next state, and part of the model predicts the next immediate reward. So everything is more or less reinforcement learning, any kind of interaction. Say you have a relationship with someone, a personal relationship, professional relationship. You are interacting with that person, right? And the person is interacting with you by perhaps changing states, by giving you feedback. Okay. So, for example, you go out, like you talk, you say to your neighbor, good morning, and the neighbor says good morning. So there is a pleasant kind of polite interaction. Uh, and, and this is how it works, right? So before we know how to interact with others, we, especially as children, we may what is known as explore. So for example, we may punch the neighbor just to see, what kind of reaction am I going to get if that happens? Okay. And it's the same idea in reinforcement learning. There is this trade-off between exploration and exploitation. We can interact with the environment always in the same way, or we can try something new. And the reason why we would try something new is because we think that our current policy is suboptimal and we may want to change it. It's the same with financial markets. Okay, so I mean, a lot of people go to financial markets, they go on Amazon, they buy the book, trading in 24 hours, they read that book. Okay, they start investing or trading with their own money and they get burned, they lose all their money. Okay, they get this negative feedback and they say, okay, I didn't do it correctly. Okay, you cannot recover from every single situation, right? So this is why you don't want to explore too much. You want to have some reasonable interactions with your environment, something where you kind of explore the environment just enough so that you can improve your behavior with regards to this environment. And why would you do that? So that you can realize your goals and so that you can move towards states that are more and rewards that are more favorable to you. So, I mean, here is another example. Here's a classic example. So Phil prepares his breakfast, closely examined. Even this apparently mundane activity reveals a complex web of conditional behavior and interlocking goal-sub-goal relationships. Walking to the cupboard, opening it, selecting a cereal box, reaching for, grasping, and retrieving the box. So there is a lot going on, and much of it is going on unconsciously because Phil's mechanisms for doing all these things are hidden from Phil in Phil's unconscious. So let's look at financial examples. So say I'm a prop trader and I observe the dynamics of market securities, and I watch economic releases. I watch news unfold on Bloomberg, and based on this information, I consider both the tactical and strategic information. I want to place buy and sell orders. Those are my actions. I want to place stop losses and stop gains. Those are also my actions. And my goal is to have a strong P&L. I may be a vanilla options market maker. So in this case, what I'm doing, I'm selling my services to people. I'm saying, look, I'm going to manufacture this options contract for you. So I'm going to start producing two-sided quotes in FX options. So I'm going to hedge my options. And here, I don't necessarily want to prop, I don't necessarily want to speculate. I want to have a hedging strategy that perfectly replicates the options contract. So because the market moves all the time, I have to keep an eye on delta, gamma, and vega, which keep changing. So that's the state. That's the market state. The market maker's goal is to hedge the position as safely and as cheaply as possible. Okay, so that is another example of a system that is effectively a reinforcement learning system. You may say, well, the original papers, I mean, the original papers were written using a different language. They were using the language of finance. But if you read them carefully, the language that they used in those papers is the language of optimal control. And those of you who have some background in optimal control know that you will end up solving these complex equations, Hamilton, Jacobi, Bellman type equations, and that it's very labor intensive. It's not an easy thing to solve those equations. So what reinforcement learning does, it says, look, I mean, you may not be able to write down that Hamilton, Jacobi, Bellman equation. It can be quite tricky, but I can give you methods, I can give you algorithms, I can show you how to solve this in nearly every environment. It doesn't have to be a well-behaved environment. I can give you an algorithm that, okay, well, but let's think about how these algorithms are structured. So the early ideas, if you look at the work by Donald Michie, so he was playing tic-tac-toe or noughts and crosses, depending on how you call that game. It's a sequential decision process. So sooner or later, the sequence of choices terminates in an outcome to which a value is attached, according to whether the game has been won, drawn, or lost. And what we do then, if the player is able to learn from experience, the choices which have led up to a given outcome receive reinforcements in the light of the outcome value. So in general, positive outcomes are fed back in the form of positive reinforcements. That is to say, the choices belonging to the successful sequence become more probable on later recurrence of the same situations. And similarly, negative outcomes are fed back as negative reinforcements. So this is an example of early reinforcement learning. This is trial and error learning through rewards. Okay, so observations and animals agree with common sense in suggesting that the strength of reinforcement becomes less as we proceed backwards along the loop from the terminus towards the origin. So this provides an adequate conceptual basis for a trial and error learning device, provided that the total number of choice points which can be encountered is small enough for them to be individual listed. So we're in this world of tabular reinforcement learning. We can just build a table and we can start updating the values of states and state action pairs in that table. Reinforcement learning was classically applied to checkers by Samuels. So I'm not going to go into detail of that because you guys presumably want to apply this to finance. There is a series of papers from the 1960s that if you want to see how reinforcement learning developed, I recommend that you read those papers. So for example, there's some studies in machine learning using the game of checkers. So that's interesting to read. It was then applied by a guy called Tessera in the 1990s to the game of backgammon, again with a lot of success. And this is where some of the algorithms, such as the temporal difference learning algorithms, were developed. So then we go for the TD Gammon. I mean, if you want to read that, that's an interesting paper to read from 1994. 1995, temporal difference learning with TD Gammon and extension. And then the huge thing that followed was the game of Go. And this is where DeepMind became, incredibly famous and incredibly popular Well, I mean, probably not as popular as some of the influencers, I don't know, like Justin Bieber or Kim Kardashian, but by scientific standards, they became very popular. It's about as popular as you get. So the 100 people who understand what you are doing actually care about what you have done. So that was the game of Go, moment of glory. And it's when reinforcement learning, precisely the algorithms that I described to you here, they beat the world champion at the game of Go. So that was even more impressive than Deep Blue beating Gary Kasparov because the game of Go is more complex than the game of chess. It has a bigger state space, okay? And it was generally believed that it cannot be solved using any means, that there is basically no way to consider such an enormous state space. Because I mean, people like to quote this: the number of states in the game of Go is larger than the number of atoms in the universe. Okay, so it's bigger in a sense. This game is bigger than the universe. Nonetheless, it was solved using precisely the methods that I'm describing here, to the point that um, the grandmaster of Go, which is similar to kind of in ranking to the grandmaster of chess, he actually retired. He said, like, look, I mean, there is no point in me continuing what I'm doing because I'm constantly outperformed by machines, and it's a matter of honor, to be sort of at the top of the game. So he actually retired as a consequence of this. The papers that you want to read is Mastering the Game of Go with Deep Neural Networks and Research by DeepMind. This paper was in Nature, and this game of Go combined the algorithms of reinforcement learning with human knowledge, with some expert knowledge. Okay, so you can have a massive database of games which was played by, if you play chess, like you can buy these books with openings, and even a human player would go through the openings, right? So you kind of divide the game into the opening, so the mid stage and the end spiel, and you kind of start studying the openings, right? But computers don't have to do this because after AlphaGo, the system that was developed in this previous paper, they developed AlphaZero, which doesn't use any prior information. Okay, and it can still outperform the best human players. So it doesn't need to watch humans play um, to come up with optimal strategies, which is kind of a bit scary because later on, DeepMind developed this next system, which is the MuZero, which is a learning system that can learn optimally and very quickly in arbitrary environments. Okay, so this is where it gets very scary. So as a human, I find this scary because I know that my problem solving abilities are very limited, right? I would struggle in a game of chess, even with, with a strong but not necessarily world class player. And this stuff, this software can learn to outperform humans very easily, right? So it's a fairly generic problem-solving equipment. So basically, then we have Watson's daily double wagering that was also beaten in the 2010s. So there is a paper, Simulation Learning and Optimization Techniques in Watson's Game Strategies. Another paper on the same subject, sort of a follow-up paper, Analysis of Watson's Strategies of Playing Jeopardy. And then we have this very interesting thing, Atari games. Why is it interesting? Because the input is sensory, right? So the computer doesn't know anything about the game apart from what you see through your senses. And this was an application of convolutional neural nets, which are used in computer vision. So all you do, you just watch the screen, you take some actions, and you learn to maximize the score. Okay, using reinforcement learning. So this is a groundbreaking paper. It's actually very, very easy mathematically, playing Atari with deep reinforcement learning. Okay, so it was a very exciting paper when it came out, and it basically showed that computers can now act optimally, not just on the basis of games, something tabular, where you have a table of states, but you can actually have sensory input, and this input space is enormous because even if you just look at Atari, the number of pixels and the possible colors, it's an enormous state space again. And then we have human level control through deep reinforcement learning that came in 2015, again using this idea of deep Q networks. And now, like before you actually do something, right? I mean, like say you go online and this thing actually like the computer knows what you're going to buy on Amazon, right? So they know like the next, I don't know, that when you want to buy a laptop, they know that you're about to buy it. So they'll tell you, oh, do you want to buy this laptop? You say, oh, how does it know? Okay, I mean, how does it know I'm going on vacation and things like that? I mean, all these things, this is personalized web services. They use this predictive power of reinforcement learning, and that's precisely the paradigm of reinforcement learning to kind of to try and optimize the services that are being provided to you, right? So there are these papers, for example, which look at how to optimize the personalized ad recommendation and increase the click-through rate through reinforcement learning. You can have a physical system, such as, for example, a data center, and you want to cool it using minimal energy, right? So that's also a reinforcement learning problem, and it's kind of solved in a lot of detail. How do you optimally control memory? How do you optimally predict branches in assembly? How do you do all this, right? Self-organizing memory controllers using reinforcement learning, a dynamic multi-core resource management and machine learning approach. How do you optimally route packets through the network that you haven't seen before? These kind of questions you can address using reinforcement learning. How do you build a robot that navigates an unfamiliar environment? Perhaps you would use some sort of a combination of SLAM, simultaneous localization and mapping, and reinforcement learning, perhaps some Kalman or particle filter based sensors. And these things are now routinely winning RoboCup soccer. And if you have watched drone races, these things now move at astounding speeds. Okay, they drive, they fly faster than a Ferrari car and so on. Let me just make sure that I don't overrun. How much time do I have?
I think you can take another 2 or 3 minutes, and then we can start the Q&A.
Okay, so self-driving cars. And I'm just trying to give you the flavor, thermal soaring. But let me give you, again, there are some nice videos of autonomous helicopter flight. Let me go back to financial applications in these remaining 2, 3 minutes. And let me actually tell you some of the papers that I have either read or written on this subject. So if you are interested in what you can do in finance with this, go for Modern Perspectives and Reinforcement Learning in Finance by Coleman Ritter. There is a series of papers by my co-authors Dixon and Halperin on QLBS, QLearner, the Black-Scholes-Merton worlds, and so on. There is RL hedging. How do you use this to hedge options? Dynamic replication and hedging, again by Coleman Ritter. There is deep hedging by Bilokon and Teichmann, Wood, Mochen, and Kochams. So that's another interesting paper to read if you want to understand how to use reinforcement learning to optimally hedge options in the presence of frictions. There's a different approach by Couch and Hull and Poulos, deep hedging of derivatives using reinforcement learning. There is an application to wealth management by Dixon and Halperin, G. Lerner and Girl, goal-based wealth management with reinforcement learning. There is optimal execution. How do you optimally execute a large transaction? Ninglin and Jamangal. I mean, this is the double deep Q learning for optimal execution, a classical paper on this subject. Optimal order placement by Schnaubelt. Again, another reinforcement learning based paper. This is the work of my student. He managed to beat existing benchmarks, and building on the work by Jim Mungle and others, he produced distributional reinforcement learning for optimal execution. This is the book that you definitely want to read. This is the classic on the subject, Sutton Barter, Reinforcement Learning and Introduction. Shepeshwari's book, Algorithms for Reinforcement Learning, that's another thing that you definitely want to consult. If you want to build connections between reinforcement learning and optimal control, the more classical approaches, such as the Black-Scholes approach, then you can read the books by Dimitri Bertsekas. There is a new book which still is being produced, is the RL theory book by Agarwal, Jankakade, and Son. And again, this is something that I recommend. This is kind of state of the art. There are these practical books by Pact on deep reinforcement learning. Again, highly recommended. Manning Zion Brown, also highly recommended. There's a book that Ica wrote with Matthew Dixon and Igor Halperin, Machine Learning in Finance from Theory to Practice. Now, that covers not just reinforcement learning, that covers the full background, the full mathematical background and algorithms that you need to eventually start applying reinforcement learning, which is considered in the final third part of the book, but it considers all machine learning algorithms as they are applied to finance. And if you're interested in big data, I co-authored another book with Novotny, Galiotis, and Deleuze, Machine Learning and Big Data with KDB plus Q, where you work with petabytes of data. This is the kind of stuff that I usually show my students on multi-armed bandits, which is a key paradigm that you start with in reinforcement learning, Markov decision process, dynamic programming. And yeah, I mean, I think that I don't want to bore you. I just want to give you some sort of a taster for the subject, right? And explain what you can do with it in practice. So I think at this point I can stop and I can ask you if you have any questions.
Great, great. Paul, that was quite something. We covered like nearly the whole history of reinforcement learning, right from
History
Newtonian
of the world.
mechanics. So yeah, it was quite fun. All right, so I'm going to lob a few questions at you. There are obviously like a lot more questions than we can possibly handle, but I'm just picking a few of the interesting ones. So I'm going to read it out to you. So Hadi Sayed Hussaini asks, typically machine learning is used to detect patterns and it works well when the signal to noise ratio is not so low. In trading, this is not usually the case. Uh, can reinforcement learning be useful uh, in trading? That's what he's
Oh,
asking.
absolutely, yeah. The only thing that you need to take into account, I mean, is these properties of finance as an application area, that you have very low signal to noise ratio, and you also have non-stationarity, right? So, but this is not the only area where this is the case. You have this in life sciences. You have this to some extent, even in some physical applications where there is a significant level of stochasticity. So yeah, this is a property of financial time series. But if you go to my SSRN page, if you just Google Paul Bilokon space SSRN, S for Sierra, S for Sierra, R for Romeo, N for November, you will see, especially the papers that I produced this year, explain how to deal with non-stationarity in the presence of low signal to noise ratio. So there are a few papers that I have recently produced that show that yes, sometimes you want to adapt these techniques to the low signal to noise ratio environment and non-stationary environments.
Right. Cool. So Ufuk asks, can we give features that we use from supervised learning, like the solution of PDEs or Black-Scholes to guide reinforcement agents?
Yes, yes. So you can, for example, one of the sources of information you can learn, for example, from the Black-Scholes model, right? So you can implement your classical PDE solver, and you can use it to train a reinforcement learning solver. But then what you can do, because the Black-Scholes solver isn't imperfect, you can use it. You can then use the real environment to fine tune and improve the learning of your model. So you can actually start by using a classical model, and then you can use the real environment to fine tune the training.
Right. Great. Okay, so this next question is slightly more generic. It comes from Fevzi Haskell. So he says there's like a lot of information out there and there's a lot of code, but he says that from his professional experience, application differs from theory. Uh, you need too much of coding experience and mathematical approach for credible results. Do you really think that accessible materials can help master the field? And what should I do more to progress with ML tools?
Yeah. So if you are doing this in practice, you want to be very, very good at programming, right? So you need to be able to code very, very quickly. And well, I mean, it's interesting that quite a few people in reinforcement learning area come from software development, right? My early experience at Morgan Stanley, I was a software developer, and I was writing tens of thousands of lines of code per day, right, before I kind of moved into data science. And you will see that David Silver, the one of the co-inventors of AlphaGo and AlphaZero, and a prolific academic, who has produced a lot of research output. He was a video game developer, right? So a lot of you do need to, if you want to work with data, you do want to program very, very quickly and very efficiently.
Okay, great. So this is a question that's come from YouTube, from David Sparks. He says that he has a model. Uh, it's got 100 different signals defined by 50 variables. I assume that selecting markets and selecting signals is a categorization model. That's what he
Uh,
says.
okay, so you can view it in different ways. The classical way of looking at it is as a problem of feature selection. Why? Because you have the canonical bias variance trade-off. You can use all your features. You can train the model on all of your features, all hundreds of those features, but it will also increase the noise. Okay, so there are several techniques where you actually start pruning those features out, and by doing this, you kind of trade off some of the variance, you get rid of some of the variance, but you may introduce bias. So a good feature selection algorithm will prevent this jump in bias, but will give you the improvement in the mean squared error that is achieved by reducing the variance.
Right. So this is, I think, a little more, you know, to do with strategy. One of the anonymous attendees says, what sort of top three trading strategies would be good for a newbie quant researcher? Please don't talk about higher MA crossing lower MA, he says.
Okay. Well, I mean, it's actually not bad to think in those terms. Well, first of all, uh, when you look at strategies, you can, if you break down the ideas, then they will be kind of somewhere in this space between sort of, momentum and mean reversion and so on. But if you take the basic strategies from textbooks, they're unlikely to work, right? So you kind of need to think a little bit more cleverly. You really need to understand the market that you're working on. You really need to understand the data, and then you need to sort of say, okay, well, these are obvious things, and everyone knows about them, and this is why they have been basically arbitraged out because everyone is using these things and they're no longer profitable. But the ideas that you use to arrive at those strategies, so the statistical ideas, some market ideas, the notion of momentum, the notion of mean reversion, that can take you somewhere, right? So you can use inspiration from these classical strategies, and hopefully then start moving towards more sophistication. But I mean, deep learning, at least if you use it properly and if you control for complexity and overfitting, should minimize for you the need to manually select these features. But it's difficult, right? I mean, I'm not saying that deep learning is a trivial kind of pursuit.
Do you think the AUM handled by option trading strategies can be as big as mutual funds? If you see a limit, where do you think it is?
Okay, so um, the it's a very different kind of game, right? The options trading strategies and mutual funds and so on. First of all, I wouldn't recommend you guys to sell options. Okay, just to remember your hockey sticks. Remember what the downside is, right? So you don't want to expose yourself to, so for, potentially uh, unlimited downside, right? So you mean kind of the options stuff, selling options primarily, right, is more for professionals. And there is a volatility risk premium. You can collect the volatility risk premium. But you need to be very careful because you remember the classical comparison of picking pennies in front of the bulldozer, right? So you need to be very careful when you do that. And this applies to many options trading strategies. It just cannot be compared directly to this. But then, on top of that, you have kind of significantly higher fees that you can earn, right? So I wouldn't necessarily compare these two businesses as sort of equivalent. I would say that, well, these are two distinct financial businesses, types of financial businesses. But you can, and some of the things that I cited today or alluded to do refer to options as opposed to spot.
Hmm. Right. Another question from an anonymous attendee. Assuming we come up with a strategy using reinforcement learning and our opponent also comes up with the same strategy, how does the accumulation of rewards work out?
Well, it depends on the capacity of the market that where you're trading. Okay, so suppose that this strategy has a high capacity, and you are trading it in relatively small size, and your opponent is also trading it in small size. You don't really interfere with each other that much. Okay, but if the capacity of the strategy is quite low, then there may not be enough for the two of you, right? And then you will experience significant alpha decay, right? So it depends on basically how much CTAs were successful for a long time, and there were quite a few of them, and they were trading at scale, right? So they managed to get away with some strategies just persist, even if people know about them. But more often than not, the moment the strategy is publicized and there is a critical mass of people who are employing the strategy, then you can experience significant alpha decay.
We have time for maybe another few questions. Okay. So another question from YouTube. This comes from Tushar Deshmukh. He says, is there any direct equivalent to Hugging Face for reinforcement learning that offers a wide variety of easily accessible pre-trained models?
There is actually there is a product which is developed by OpenAI, the same people as people who have developed ChatGPT. It's called the OpenAI Gym. Okay, so OpenAI Gym gives you a lot of classical environments, and there are also several kind of collections of standard models. Deep Q learning, expected Sarasa, and so on. Some more advanced things that you can then start applying to these toy models from OpenAI Gym. Hopefully, get some result and move them to solve real problems out of the OpenAI Gym.
Yeah, great. There's another question from YouTube. This comes from Eventing in Seattle, who says, how could I use machine learning to do fundamental analysis for value investing using the Graham Dodd, Warren Buffett style to
Yeah.
find high quality stocks that are undervalued?
Well, nowadays it's becoming much easier than it used to be because you have the LLMs, and the LLMs can process a lot of unstructured data, including textual data. So you can basically set up something like LangChain, a system that sits on top of an LLM and automates the data processing flow within the LLM. Then you need to source the data that you want to look at, this fundamental data, which would probably come in the form of some PDFs. And you can then feed it to your LLM using, for instance, LangChain, right? So definitely, nowadays you have tools that allow you to perform fundamental analysis and also kind of alternative data type analysis.
So I think so I'm going to just tell you the last couple of comments. Many people have asked whether they can get access to this presentation.
Uh, I can send you this presentation so you can
Sure.
distribute it.
Great. And I think there were also a number of people who wanted to know where they can pick up the papers that you referenced through the presentation.
If you Google my SSRN page, some of my papers are in open access on SSRN. So if you basically
Okay.
just go to, let me just see if I can If you just Google my name like this, you can find quite a few of those papers there. Some of them are not there because, if they're published in, say, Journal of Financial Data Science, they require me to take the preprints down. Some of the publications do require that. Um, and also the book on Amazon, which is Machine Learning in Finance, that contains a much more extended um, view of this, um, and you can find things there. But I mean, my recent papers, my recent research, much of it you can find in my SSRN page.
Perfect. Great. I think we've managed to cover a lot of questions. So that's great, Paul. Thank you so much for your time. I think the session was wonderful and the Q&A was even more fun.
Thank you very much. I've enjoyed it
So
as well. Have a good day.